So welcome to our first video about ellipses. Hopefully I'll be able to keep to just one video, but I want to be thorough and not skip out on anything. So we have a few different pictures up here. They look kind of like beans or eggs or squished circles. They are my best rendition of an ellipse. Ellipses, very straightforward, look like circles that have been deformed slightly. In fact, circles are a special type of ellipse, but we're not going to go into that right now. I'm not writing down the definition. It is written down in the notes that accompany these videos, but I do want to say the definition. So the ellipse is the set of all points, so this graph, the sum of whose distances to two distinct fixed points, each of which is called a focus, is always constant. So no matter what point along this shape I pick, if I draw a line to the first focus and then the second focus, and then I add those two distances together, it's always the same number for that ellipse. That number will change, or at least may change, from ellipse to ellipse. But for the same ellipse, all of these points along the, for lack of a better word, the circumference of this shape, have the same distance, the same sum of the distances to the two focus points. I almost said focuses, but that is incorrect. The proper plural of focus is foci. In my very first college math class, which was Precalculus, my teacher was very adamant that it is pronounced foci and not foci, as many people want to give that C a hard sound. I'm not a Latin speaker, even though I did study Latin a bit in high school. Regardless, generally mathematicians will say foci as the plural of focus. There's a couple other things that ellipses have in terms of vocabulary that we need to build. So the long distance across the ellipse is called the major axis. The short distance is called the minor axis. In a sense, these are like a circle. It's been squished a bit, so now it has two different diameters. There's the shortest diameter and the largest diameter. It's not a very accurate way of, well, it's not a very precise way of explaining what these are, but it is a very accurate way of helping us relate what we know about circles to what we're learning about ellipses. So it's as if the ellipse has two different diameters, a short one and a long one, which might lead you to think, does an ellipse also, by that analogy, have two different radii? And we can say it does. So from the center, halfway along the major axis, is a distance that we often label A, because major axis, it comes first. Half the distance of our minor axis, so from the center of the ellipse to the ellipse itself, this is a quantity we call B. And so for every ellipse, whether they're squished flat or squished skinny and tall, A is always going to be the major half of the major axis. So to just illustrate, we could have an ellipse that's kind of shaped like this, where in this case, A is the up and down distance, and B is the left and right distance because it's been squished the other way. We are not going to go into ellipses that are tilted on a diagonal. We certainly can do that, they exist, but we usually keep to right-angled ellipses in that the major and minor axes are always vertical and horizontal, nothing on the diagonal. So this is a quick overview of some of the vocabulary of ellipses. Before we go on and start looking at equations, I encourage you to pause the video, sketch this down into your notes, because in about 2 seconds, I am going to erase it all. So here we go. Ellipses have two different equations. It's incredibly annoying, but they share enough similarity that if you understand the form of one of the equations, you'll automatically understand the form of the other. So ellipses start off looking very much like circles, in that we have the x minus h squared, the y minus k squared, and so the center is still going to be at h comma k, just like for our circles. But this is where there's a slight change, because we divide our x term by a squared, and we divide our y term by b squared, and then our equation is always equal to 1. Because we said that the sum of the distances is always equal to 1. But we said more precisely it's always equal to a constant, and how that shows up in the equation is that it's just a constant 1. This gives us an ellipse that is oriented more wide. So this is what I call a horizontal ellipse, because the major axis is horizontal. Now notice that the A, which goes with the major axis, is with the x term. And if we think of the direction of the x-axis, it's left and right. So we can measure from the center, left or right. This is the distance A. The y term, on the other hand, describes distance moving up and down. So we get the up and down distance being b, which is always the smaller one. But we also said on the last slide, for lack of a better word, that we can have ellipses that are vertical and not horizontal. So a vertical ellipse looks like this. We'll have the A going up and down and the B going left and right. So we're going to get a very similar equation, but with one key difference. Rather than dividing x by a squared, as we did first, it's going to be b squared, because this time b is the distance that's going left and right in the same direction as our x. Likewise, our y term will get a squared, because the up and down distance in the y direction is the bigger number in this case, which is a. And as before, it all equals 1. So take a moment, write this down, because there is still one important thing that we need to discuss. And that is, we know that the definition involves these 2 points that's each called a focus, and they're fixed points, they're not moving. But where are those points in the ellipse? And so approximately those 2 points would be somewhere in there. If I failed to mention it earlier, the foci of an ellipse are always points on the major axis. So as we take our 2 foci and move them farther apart, we're stretching out the ellipse in that direction, or we could be stretching it up and down. So they're always along the major axis. And so there's this third quantity called focal length. So if I draw this ellipse again, here's our center, here are the two foci. That distance from the center to a focus we call C, and the formula for an ellipse, which comes from a lot of drawing triangles, and it can get very involved, and we're not going to go into it in this video. We find that A, B, and C have a relationship. C squared is equal to A squared minus B squared. This sounds a lot like the Pythagorean theorem, but it is not. We know that C squared, because the foci are inside the ellipse, we know that C needs to be smaller than A. And we know that A is always bigger than B. We also know we can't have a square root of a negative number. So that logically says, well, if C has to be smaller than A, then we have to remove something from A squared before we take the square root of it to get C. That by no means is a proof of this, but it does help relate it to some logical ideas that will make it, hopefully, will make it easier to remember this formula. Because later on when we get to hyperbolas, our focal length formula will be different. So remembering for an ellipse that the focal length is shorter than A will hopefully help you remember that we subtract B squared. So again, take a moment, write down these formulas, including for the focal length, and then on the next slide, in a moment, we will graph an ellipse using the equation. So I'm assuming by now you've written that all down. So I'm going to erase all of this and make space because we'll need this space. Okay, so I'm going to just randomly pick some numbers. So let's do -1 here over 25 plus, let's do y plus 2 squared over, no, I'll pick an easy square number. How about 9? And it's all equal to 1. So this is our equation that we're now going to graph. The first thing we want to do is identify the center. So just as when we were looking at a circle, we'll look at x minus 1. So 1 is the x coordinate. Then we have y plus 2, so -2 is the y coordinate, and that gives us our center. Y, 1 comma -2. Then we have to compare 25 and 9. Whichever one is bigger gets to be called A squared specifically. So that means 25 is A squared and 9 is B squared. So A is equal to 5 and B is equal to 3. Pretty straightforward so far. We also need to find the focal length. So we know that C squared is equal to 25 A squared minus 9, which is B squared. And 25 minus 9 is 16. And so C is 4. Yes, it's convenient that I picked a Pythagorean triple without realizing it. Anyways, moving on. This is the information that we're going to use to help graph our ellipse. And so I need to sketch out a coordinate plane. And so we're going to start by plotting the center, just as we did with a circle. And so I'll go 1, and then down 2. So this is the center. And I usually try to label the points. So I put a little C next to center. I'll use points like V for vertex, or that reminds me, I didn't define the vertex. Well, we'll get to that in a moment. So in fact, that's where we are. The vertex are the endpoints of the major axis. So in this case, because our major axis, our a squared, is with x, our major axis will be horizontal. And each of those vertices is 5 units to the left and the right of our center. So I'm going to count out 1, 2, 3, 4, 5 more points. And I'm going to label that point the vertex. Then I'm going to count 5 points in the other direction. So that's 1, 2, 3, 4, 5. This is our other vertex. So again, I'm counting from the center. So notice that the y value of these points did not change because we're just moving left and right. To show the foci, we're going to do the same thing, but with 4. So it'll be right here, that's one focus, and over here is the other focus. So if we wanted to describe these points, our 2 foci, notice that the x value changes. It's 1 minus 4, which would be -3, comma, -2, which is the y coordinate of the center. And then 1 plus 4 gives us 5, comma, -2. So these are the 2 foci. So that checks off using A and C. So now we have to use B. Because B was with our y term, telling us how far to go up and down from the center. So we're going to count up 1, 2, 3 spaces, and then down 1, 2, 3 spaces. Notice that I did not label these points. They are technically not vertices. I have at times heard them referred to as co-vertices, but we don't need to worry about labeling them. We just need to have them there. Because just as once we got to this stage with a circle, we connected all the dots, that's really what we have to do now. So we end up with this shape. Anything hand-drawn is most likely going to be a little bit lumpy and look more like a potato than a perfect ellipse, and that's okay. Things that we don't want to do. We do not want a corner. It should not look like an eye slightly waking up. We do not want these sharp edges. We want to make sure that we're drawing something smoother that has no corners, which is very similar to how we wanted that smoothness with our polynomials. In fact, all of these conic sections we can say are polynomials. They're just polynomials in 2 variables, x and y, which is very different from the polynomials that we studied in our last unit, which were polynomials in 1 variable, which also meant they were functions, whereas this is not a function. It fails the vertical line test, not a function, but it is still, in the technical sense, a polynomial. This is really the steps to graph an ellipse. These problems can take a little bit of time. I don't want to make this video too long, but there are additional examples if you look in the written notes that have significantly more details written out than what I've put here. So if you need that extra resource, it's available in Google Classroom. You can also attend Zoom classes in the afternoons as well.